Good day, and welcome to this session of the Cloud Technical Series on event-driven architectures. My name is Prasanna Kenny. I'm a customer engineer specializing on data and analytics. In the session today, we shall be looking at the difference in perspective between a data-driven approach and an events-driven approach to solution design. We shall be looking at examples of event-driven architectures on Google Cloud, and I shall then walk you through how we build an interactive pipeline using streaming financial transactions on Google Cloud. So let's get started. We've heard so much about data driven organizations, data driven transformations. So let's think about a traditional data rich event, a transaction. So let's assume a scenario here where we have a customer who's been looking for a product, who sees an ad, and then goes on to make a purchase. Now, this transaction generates a lot of rich data. What was the product that was bought, at what price, what location, via what channel, what were the discounts that were offered, and therefore what was the margin associated with it. And this information then adds to what we already know about this customer in terms of the customer's purchase history, in terms of the customer's interests, perhaps. And this transaction then goes on to roll up into financial performance views, into marketing performance, maybe with a focus on return on advertising spend, and into inventory views as well. This, therefore, is a data rich event. But when you think about it, isn't there a whole funnel that goes into making this purchase? If we look at the journey that the customer went through, right, from awareness to consideration to evaluation to the actual purchase decision, and what were the systems at work behind the scenes to nudge the customer onto that decision, right from the time the customer started doing some online research, perhaps using Google search, the signals that indicated that the customer was in market looking for a product, and perhaps made the customer part of in market audiences, enabling the customer to receive very specific targeting ads. The ad impression events that were generated, the conversion events, and then when the customer ultimately clicked on that ad and visited the brand's digital property, the whole set of clickstream events and the online behavioral patterns. There could have been remarketing, retargeting that happened when the customer left the digital property after the first and after the second visit. There was the personalization that probably happened when the customer spent time on the organization's digital properties. So, if you think about it, it was a whole event driven system at work to make this one purchase happen. And while we looked at marketing and personalization as an example, there's a wide range of opportunities where event driven solutions can deliver immense value, such as customer service differentiation, straight through processing journeys, fraud detection, process optimization, or solutions that can help you prevent or mitigate loss. Now, while these opportunities are high value, there is a limited time window associated with them. So, how do we address the vanishing window of opportunity presented by these events? Traditionally, when we've been implementing streaming analytics solutions, these have been perceived as complex for a number of reasons. Firstly, there's the need for a robust ingestion service to be able to reliably ingest events and deliver them to multiple subscribers. The traditional approach has been to use Lambda architectures, which come with the architectural burden of maintaining a separate pathway for batch processing and for streaming processing. There's the need to have a serverless architecture which can then seamlessly scale up as the number of events per second increase and then decrease over a period of time. And then there's the ability to be able to do complex event processing through transformations such as applying various kinds of windowing functions, be it rolling windows, be it fixed windows, the ability to be able to do window computations on top of the stream, etc. And then when we're talking about scoring these events as they come in, there's the ability to be able to do low latency model serving and low latency feature serving as well. Now let's look at how are these requirements addressed on Google Cloud. So what you see here on the screen now is a very typical architecture pattern that is implemented for stream processing on Google Cloud. We have the events on the left feeding into an asynchronous message service called PubSub. The next service that comes to the right of PubSub is Dataflow. Dataflow is where stream transformations happen in terms of windowing, in terms of doing window computations, in terms of looking at the high watermark, etc. This is where you could also be using a machine learning model to score the events as they come in. And then from Dataflow, we are writing in this example to two sinks. We are writing to BigQuery, which is acting as the data platform. And perhaps we are also writing to an actions queue, which is another PubSub topic. Now, each one of these components are very, very unique. So if you look at PubSub, there is no provisioning of PubSub at all. It's completely serverless. There are no shards, there are no partitions, there are no brokers. You just create a topic, publish, and start consuming. It scales global data delivery automatically from 0 to millions of messages per second. Coming to data flow, we spoke earlier about the architecture overhead of maintaining separate pathways for stream and batch processing. What Dataflow offers you is a unified stream and batch processing that's again completely serverless, fast, and cost effective. Importantly, it separates the logical design of the pipelines from the optimal execution, which means that it allows your teams to focus on business logic rather than having to manage infrastructure or manage clusters. Dataflow takes care of auto-scaling resources and even dynamically rebalancing work across workers in the middle of a job. It's based on Apache Beam, and one of the important tenets of Beam has been interoperability between different SDKs and different runners. So you could choose between Java, Python, Go, SQL for developing your pipelines. And for the runners, you could choose between Spark, Flink, or Dataflow on Google Cloud. And coming to BigQuery, you would have heard a lot about BigQuery in the session earlier today. But the important aspect that I'd like to focus on is how BigQuery can ingest data at extremely high volumes and low latency. So you could be inserting data into BigQuery at very high speed, very high volumes. And importantly, this data becomes immediately available for query. So let's look at an example here where I'll switch on to a demonstration and we'll build an entire pipeline just like the one that you see on the screen right now. We'll simulate some events which are financial transactions. We'll write them into a PubSub topic, and I'll interactively develop with you a data flow pipeline which reads from the PubSub queue. Maybe we'll do some windowing, etc. And then we'll write the output into the BigQuery data platform and then perhaps also into a PubSub topic. So let's get started. So what you see on the screen right now is PubSub. So let's start by creating a topic. Let's give in the name of the topic here. We'll call it CTS underscore transactions. I'll check here that I want to add a default subscription and I'll say create a topic. So as I mentioned to you earlier, this is practically as simple as it is. There are no partitions, there are no shards to manage. It's simply a question of creating a topic and then starting to send data onto this topic. Yeah, and a topic is now created. As you can see, since we asked for a default subscription to be created, we have the subscription available here as well. The next thing that we'll do is we'll start simulating certain real-time transactions which can write into this topic. Now that typically has been a challenge in terms of how do we simulate a stream of transactions. And this is where we have Dataflow to the rescue, where we have a wonderful utility from Dataflow which can help you create and simulate such transactions. So let's move to Dataflow. This is your first look at Dataflow. And what we're going to be doing here is we're going to create a job from a template. I'm going to call this as the CTS transaction generator. And there are a number of templates that are available to me from Dataflow for a variety of pipelines, right? So I could be taking data from Spanner into BigQuery. I could be using DLP to do data masking or tokenization. I could be moving data from Kafka to BigQuery and so forth. But the template that we're going to be using right now is this one here, which is called as the streaming data generator. There are a couple of parameters that we'll need to specify. So this is where we can specify the number of transactions per second. So we could specify maybe 10, 100, 3000 transactions per second, and Dataflow will generate those many queries per second for us. And then I can specify some optional parameters here. So I can specify what is the schema I want these transactions to have. So I've created a schema file already and kept it on cloud storage, which I'm going to select here. This here is my JSON schema file, and I'm going to select the topic. So this is the topic, if you remember, that we just created in the last step called CTS transactions. And that's pretty much it. I can then set this data flow job running, and this will then start generating these transactions into my topic. What we shall then do is we shall go to the topic again, and we shall look at these transactions being written into the PubSub queue. So I'm going to go to this subscription here. I'm going to messages, and I'm going to pull some of these messages so that we can inspect them. So it's pulled a few messages from the topic queue, and let's just take a look at one of these as an example. So this, as you see here, is the schema that I'd specified. So these messages have a transaction ID, it has a transaction timestamp, it has a customer ID, the transaction amounts, the type of transaction in terms of credit or debit, and also the channel through which this transaction originated. So in this case, it was branch for most of these transactions. And here I have an example of internet banking. So what we have so far is we have a stream that's been created of financial transactions being written into a PubSub queue. Now, the next step that we're going to be doing is we're going to be creating a data flow pipeline interactively. We're going to be reading from the PubSub queue, and we're going to be doing some transformations such as windowing. So let's move on. Now, there are a number of ways in which I could create a data flow pipeline. In this case, what I'm using is I'm going to be using a JupyterLab notebook, and I'm going to be using what we call as interactive beam to be able to interactively build this pipeline. What that enables me to do is it enables me to execute various commands and then immediately look at the responses. So for instance, when I pull in data into what we call as a P collection, I can then inspect what that P collection looks like. I can inspect what my windowing function applied to that P collection has resulted in, etc. So let's get started. I'm going to start by importing certain libraries. I've specified here the topic, the CTS underscore transactions topic that we're going to be reading from. I'm specifying some options here. And then importantly, this here is the recording duration. Now, why do we need a recording duration? Because we are dealing with an unbounded data source. And for us to be able to play with the data, to be able to replay the data, we need to specify a window which Interactive Beam is going to record. And then it's going to be the data within that recording window that will be available for us to replay. So I've specified the recording duration here as 2 minutes or 120 seconds. I'm going to choose the interactive runner. So here I've listed 3 different options where you would have a choice of using a direct runner if you want to validate your pipeline during development. This executes your pipeline on your local machine. I have the option of using interactive runner, which we're doing right now, where I can then use this pipeline interactively in a notebook. And the third option is once I'm ready with my pipeline, I can then submit it to a data flow runner, which executes my code and dependencies onto a GCS bucket, and then creates a data flow job, which executes on managed resources on Google Cloud. So this is where I create a pipeline using the interactive runner. And then the next step is where we're going to be reading from PubSub. So here we're using the beam.io function for reading from PubSub. I've specified the topic here, and I've specified the map function because this is JSON data. This is the data that I've now read from the PubSub queue. So the same schema that we looked at earlier in terms of the transaction ID, the transaction timestamp, and so forth. We'll move on then to do some transformation. So in this case, the first thing that we'll do is we'll do windowing. Let me just stop this cell here so that we can proceed. So I'm going to be doing a bit of windowing here. So I'm going to be choosing between fixed windows and sliding windows. So fixed windows in this case is, let's say if I choose a 10-second duration, then these are fixed windows of every 10-second duration. And a sliding window would mean that I have windows of 10 seconds, but with a slide of 1 second each. So in this case, I have code here available for both, but I'm going to go with fixed windows because sometimes sliding windows can get a little bit confusing because you will have the same transaction surfacing in multiple windows as the windows slide across that time frame. So we're going ahead for the purpose of this demonstration with fixed windows of 10 seconds, and we shall look at these windows, how those transactions are grouped among these windows. So as you can see now, what we're doing is we're retrieving these transactions, so the individual transactions, and we're also looking at the window associated with it. right? So in this case, for instance, we are looking at 28 minutes and 40 seconds past it. So this is the window here, and then let's say if I move forward, this is where we moved on to the next window, which is 50 seconds past 28 minutes. And then we can visualize this data as well. So in this case, for instance, I may choose maybe the channel in terms of binning the x-axis. I could be binning the y-axis based on perhaps my windows. I have about 13 windows here because I have a window uh, of 2 minutes, and then I could also color this perhaps by the channel, right? And or I could color this by the transaction type, right? So immediately I have my visualization available here in terms of how these data points are spread across windows. I have my 40 seconds, 50 seconds, 10 seconds, 20 seconds, and so forth, and how they're distributed across channels. And then I could select any one of these data points and I can get a full view in terms of what went into this data point. So to recap, what we've done so far is we read from PubSub, we've done a fixed windows of 10 seconds each, and then we've done some visualization to analyze this data. What we'll move on next to do is we'll do some window calculations. So we're going to be calculating a run rate. So we're going to be extracting the transaction amount from these windows, and then we're going to be summing up the transaction amount for every window. So the first step here is we extract the transaction sums, and then we calculate the run rate by using this transform here, which is called combine globally and doing a summation. And then let's inspect this data. So what this has done now is this has done an aggregation. So I'll be able to see the total transaction amount for each of the windows that I was looking at. So if you look at this, this is the first window, which is 40 seconds past 28 minutes, and this is the summation available. And then I have the windows getting added here in terms of 50 seconds and 29 minutes, 0 seconds, 29 minutes, 10 seconds, and so forth. And then once I'm finished processing for all of these windows, we'll just look at a visualization here as well. And once we're done with this, what we can then do is once we've built a pipeline, we can then add a sink. In this case, we will use BigQuery as a sink. And then we can start running this pipeline on Dataflow so that it runs on the GCP managed resources. But let's first do a bit of visualization here. And I've used a pie plot here to look at what's the distribution across all of my windows. So the next thing we'll do, now that we've developed this pipeline interactively, we've done windowing calculations and aggregations, I'm going to be now creating a BigQuery sink. So in this case, I've defined my BigQuery table. I've specified my project, which data set it belongs to, and which table. And I then use my beam.io to write to BigQuery. And then finally, I choose the Dataflow runner. So I'm switching here from the interactive runner to the Dataflow runner. I'm going to set the options for the Dataflow runner, such as specifying which region this pipeline should run in, what should be the GCS location to stage the data, etc. And then I'm all set to execute my pipeline. So this is where I'm going to be using Dataflow as a runner to execute the pipeline. So one of the important things here is what Beam delivers to you is also the portability, which means that you can seamlessly then switch from one runner to another without having to change a single line of code. So it's now submitted this job to Dataflow. So if we switch over to Dataflow, we should be able to see the job running here already. I'm going to refresh the screen here, and I have my job running over here. So let's open this job and inspect what the graph execution graph for this Dataflow job looks like. And this is where I see the graph here in terms of reading from PubSub. So these are the very same cells that we looked at in the notebook, where it reads from PubSub. It has one stream here where it's writing to BigQuery. And what it's also been doing here is in this stream, it's doing some windowing, getting the transaction amounts, computing the run rate. And with this Dataflow job now inserting data into BigQuery, we can then go and start querying the data in BigQuery. So if you remember what I'd mentioned to you earlier was that as soon as this data lands into BigQuery, it is available immediately to query. So in this query, what I'm doing is I'm going against that table in BigQuery. I'm looking at the current time, and I'm also looking at what are the number of transactions in the last 10 minutes. I'm joining with my customer segments table to be able to see what was the last transaction that was executed for that combination of customer segment and channel, and also what is the total value of transactions that happened in the last 10 minutes. So let's execute this query and look at the results. Yeah, so that's the data in BigQuery. So the local time where I'm based right now is 12:05 and 17 seconds. And the last transaction that happened for this combination of customer segment, which is rural affluence and the ATM channel, was at 12 seconds past 5 minutes. These are the number of transactions that happened in the last 10 minutes, and this is the value of those transactions. So that's what I wanted to share with you. What we've looked at is we looked at creating a topic. We started writing to that topic, streaming transactions that we simulated, and then we interactively built a data flow pipeline, which read from the PubSub queue, which did some windowing, we did some calculations, and then we were able to write into BigQuery, and we were able to also query the data from BigQuery in real time. So as soon as the data landed in BigQuery, we were able to query it. So having looked at this example, let's move on. Now, what we've looked at so far was a pipeline that did stream transformations. Now, when we bring stream analytics with real-time scoring into the picture, there are additional considerations that come into the picture. Firstly, there's the need for model serving endpoints that can offer low latency model serving and auto scaling. And that's why Vertex AI comes into the picture. With the ability to be able to publish models to endpoints, and for the endpoints to be able to seamlessly scale up and down based on the transactions per second. Now, the other thing that you might want to consider is the incoming event, which is coming through PubSub, may not necessarily have all of the features that the model needs for scoring. And that's why we may need the ability to be able to look up features from like a feature store. And that feature store again needs to have the ability to be able to serve those features in low latency. And that's where we have the feature store coming into the picture. What the feature store enables you to do is it enables you to share features across the organization, and it's a managed solution for online serving at scale. Now, the feature store itself needs to have streaming updates. So, for example, when we look at a solution like transaction fraud, you may have features which look at, let's say, the total volumes for this particular customer over the last 6 months. It may have features which might also say the total transaction volumes in the last 10 minutes, in the last 5 minutes. And those are the kind of features which need to be kept current, which need to be updated in real time. And that's why you see on the left of the screen here, we have a feature engineering streaming input that goes into feature store as well. What we've shown here is now we've shown the model training pipeline. There are multiple ways in which you can train your model on Google Cloud, be it custom models, be it BigQuery ML, be it AutoML. Now, one of the important things that you'll notice here is that we've used the feature store also to supply data for the model training. And this addresses one of the important challenges with training and serving skew, which occurs when feature data distribution that you use in production differs from the feature data distribution that was used to train the model. So the feature store also provides you point-in-time lookups to fetch historical data for training. And with these point-in-time lookups, you can then be rest assured that you're fetching only the feature values that were available before a prediction and not after. To summarize, we looked at how event-driven architectures offer immense value but also come with a certain level of complexity. We then looked at event-driven architectures on Google Cloud and how these challenges are effectively addressed because of the serverless nature of these services that allow you to focus on business logic rather than having to worry about managing and scaling infrastructure. We spoke about the unique value of data flow in terms of the unified framework for stream and batch processing. And we spoke about the complete MLOps lifecycle, enabling you to implement low latency model serving, low latency feature serving, with the ability to make streaming updates to the features themselves. I hope you enjoyed the session. Have a good day.